All right, hello and welcome back. Previously, we talked about between subjects ANOVA. Now we're going to talk about the one way within subjects ANOVA, sometimes also referred to here as a repeated measures ANOVA. And so just going back to where we're at in our grand diagram here, whatever you want to call this, decision tree, we are here, right? So now we're still working with one factor, more than two groups, except now we're looking at within subjects observation. And we'll kind of hit on that a little bit if you need a refresher on what exactly we mean by that. So I'll move quickly through some of this stuff since this is review after the previous module. So a reminder here, we're talking about ANOVA, also referred to as an F-test because that's the primary statistic that we'll use to inform our final decision. And if we're looking at it within subjects ANOVA, well here, yeah, pretty much the same as last week. We're looking at one factor, two or more levels, same general hypotheses and premises, except here we're looking at the same participants and we're observing them at each level of the factor, right? And so the one factor, one way, right, that is consistent from what we did last time, except now we're looking at the same participants, right? So the same individuals over each level of the factor, whatever that may be. And so that's where that within subjects terminology comes from. We're looking for change within the individuals rather than between separate individuals. And so, yeah, same as last week. A key thing here is that the F statistic, or F obtained, is essentially the same for any one-way ANOVA, or I guess I should say the same core equation is what we'll be using on each of these one-way ANOVAs. How we arrive at the numbers for that might vary a little bit, as you'll see this week. But generally speaking, the same basic equation, the same basic premise, in that we're looking at the ratio of variance between groups to the ratio of variance between groups to variance within groups. And so here are sources of variation. There are three in, there's a typo. That should say one way within subjects ANOVA. So here we have variance between groups, within groups, and between persons. And so let's do a hypothetical example real quick. Not going to have to solve anything, but just to explain those sources of variation. So let's imagine we're working with UAF and we're conducting a study about students' sense of belonging throughout their time as a student. So in other words, from the time students, if they come here as a first year freshman, fresh person, whatever, and they stay here until graduation, we're interested in their sense of belonging throughout that entire time, right? Are we reaching people immediately? Do we give them a sense of community and let them know that they belong here, help them feel that way and recognize that? Is that consistent throughout their experience here? Are there peaks at a certain time, valleys at a certain time, right? Whatever it may be, that's our basic question here, is a sense of belonging throughout time as a student at UAF. And so we sample students from the overall population, and we just track them throughout their time here. And in each group, we're going to ask them to rate their sense of belonging on a 0 to 10 scale, right? And so, our overall population, that is UAF students, and we pull out a sample from there. And presumably, if we're doing this and tracking the same group consistently throughout their time here, then we'll get a group of first-year students, and we'll track them throughout their time, right? And so then in their first year, we have them answer these questions, rate their sense of belonging on a 0 to 10 scale. And then they do the same thing in year 2, year 3, and year 4, right? So it's the same groups pulling from the same sample, ultimately tracking that within subjects changes over time in their overall sense of belonging, right? And so to elaborate a little bit more specifically on this example, let's say we have a group of first-year students, and this first person rates their sense of belonging at 2 in their first year. Another person rates their sense of belonging at a 1, right? So it sounds like they're struggling to find some community. This person rates it as a 5, right? So we're seeing some difference, and this here we'd call within groups variance, right? And so this is variance that's due to naturally occurring differences within each group. And so here the key thing is that the groups are these times of measurement, right? Or these intervals of measurement, right? And so group one is during their first year. And so there's naturally going to be some variance within that first year experience. Some people might come with people they know, like this person that rated it a 5. Maybe they came here with some friends. Like, for example, when I was a college student, I lived with 3 of my high school buddies in the dorms our first year. And so I felt some sense of belonging right off the bat just by the fact that I was coming with people I knew. Whereas maybe this person who rated it a 1 didn't know anyone, right? And so that's an example of within groups variance here. In this case, within the first year experience. And so we track them over time. And so you can see improvements across the board here, or rises in sense of belonging, I guess, across the board here. And we track them over time. You can see third year to graduation, they feel the greatest sense of belonging. Post-graduation is still there, but it dwindles, which makes sense, right? They're no longer, or for most people, they're no longer a part of the UAF community very explicitly. Like you might work here or something like that, but it doesn't have the same maybe magic as when you're a student. And so we can calculate means for each of these groups here to assess a general trend. And those means are an example of between groups variance, right? Whereas before we were looking at variance within the individual group of the first year, now we're looking at variance between the groups as a whole, right? So the first year group mean being lower than the second year group mean, and so on, right? So it's between groups variance in this context. And then we can also calculate means here on the right. We can calculate means for each person or each subject. And so you can see person C rated the highest sense of belonging, right? And this person started out highest. So it kind of makes sense, right? Just in our basic observation of the data here. And this is an example of between persons variance, right? Whereas previously we're looking at the overall groups, so everyone in their first year compared to everyone in their second year, and so on. Now we're looking at this person throughout their time here compared to this person throughout their time here, yada, 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 right? So some key examples of the sources of variance in this one way within subjects ANOVA. Some graphics if you'd like to come back to it. Yeah, I won't spend time elaborating on it here, but I encourage you to come back and look if you'd like. Degrees of freedom. Here are total degrees of freedom is slightly different annotation. Kn minus 1, where K is the number of groups, N is the number of participants per group. And so here, the key distinction is rather than say it's big N minus 1, that could be confusing here because we have the same overall number of participants. So for example, in that previous one, we were following 3 people over time, right? So really, when we're talking about degrees of freedom total, we're talking about the total number of observations rather than just the total number of participants, because it can be confusing here since it's the same participants at each time point. So that's why we notate it this way here. And importantly, we're going to split the degrees of freedom into 3 parts, one for each source of variation. So these map on to what we just talked about. So these degrees of freedom between groups is equal to K minus 1, number of groups minus 1, that makes sense. Degrees of freedom between persons is little n minus 1, that one also makes sense. And then degrees of freedom error is simply the product of those two. So DFBG times DFBP. Or if you want to solve for that all at once, you could just do K minus 1 times N minus 1. And just to note here, these are the 2 that you'll report in your ANOVA results. Like when we do F of 2, 10, or whatever it may be, these are the numbers that we'll use for that, DFBG and DFE. Okay, so similar to before, just a little visual aid here to hopefully help understand where the degrees of freedom are coming from, or which variants they're sort of mapping onto, so to speak, or that they're connected to. So moving forward through some last logistics, hypotheses stay the same, slight change in notation. So now we use big M here instead of mu. So here we're saying that the group means do not vary in the population in our null hypothesis. And in our alternative, we're saying that the group means do vary in the population. Similar to last time, we need equivalent sample sizes for each group. Assumptions, as per usual. And let's dive into an example here. So, example 13.1. So let's say we're evaluating the effectiveness of advertisements to help teenagers stop smoking, right? So these ads that kind of come in your face and try to convince people not to smoke or to stop smoking if they are, rather. And so we have a sample of teenagers and we ask them to simply look at each ad and then rate the overall effectiveness. So if it's not at all effective, they're going to rate it a 1. If it's very effective at convincing them to stop smoking, they'd rate that a 7. And so we have our numbers here. You can see we have a few different conditions. So one ad uses words only, the no cues condition. So you can see that right here. And our participants, you can see we have, what is that, 1, 2, 3, 4, 5, 6, 7. We have 7 people, 7 participants. And you can see that each person viewed all 3 of the ads, right? And we're categorizing those ads according to cues. So this no cue condition just uses words like, hey, dipshit, stop smoking, or something like that. I mean, no offense if any of y'all are smokers. I used to use tobacco a lot myself in pretty much every way, shape, and form. So I've been there too. So I'm calling my younger self a dipshit is what I'm trying to say. And so the generic cues condition. So this, the second ad uses a generic abstract picture. Maybe I don't know. I don't know what it's of, but it's generic. It's telling you to stop smoking. Maybe it's just like a cigarette with like a red X over it or something. And then the third ad shows a picture of a teenager smoking and coughing. So these are smoking-related cues condition. We call it the smoking-related cues condition. Right, so in this case, it's very specific to smoking. It's trying to say, hey, if you smoke, you cough, it's bad for your health, so on and so forth. And so what we want to do is conduct an ANOVA at a 0.05 alpha to see if there's significant differences within persons, right, across these various cues and conditions. So let's walk through these steps. Same steps as always. First, we'll state our hypotheses. Oops. Not sure why I was doing that. Yeah, and so here, as always, right, equal to 0 greater than 0, or in this context it is. So here in our null, we're stating that the mean ratings for each advertisement do not vary between groups in the population. So in other words, each advertisement is essentially the same. There's no difference in how effective they are. And then our alternative, we're saying that there is variance, right? Some ads must do better than others or have varying levels of effectiveness in the eyes of these teenagers. And then step 2, setting the criteria, we stated alpha is 0.05. We can calculate our degrees of freedom. So 2, 6, and then the product of the 2 for DFE. And then we'll use DFBG and DFE in our F table to find our critical value of F of 3.89. And so here's what that looks like graphically. Remember the F distribution is very negatively skewed. So it just, or is this positively skewed? I get this backwards too. It's skewed towards 0, right? Whichever one that is. I'm recording this late at night, so I apologize. So we have our F distribution, our critical value of 3.89. So if we obtain an F that is greater than that, then we would reject the null hypothesis. If F is lower than that, we will retain the null hypothesis. And so let's compute that. Let's find our obtained value of F. So our basic formula here, similar to last week though, there's a lot of steps and like micro steps to this. So I'll walk through this, hopefully without insulting your intelligence and over explaining. So first, finding K and N, that's easy. K is 3 because it's number of the groups. N is 7, or little n is 7, I should be more specific, right, because we have the 7 people in each condition. Now we need to find sum of x total. And then first, sum of x is easy, right? We're just going to add up all the observed values of x. In other words, all of the individual ratings of effectiveness of each of the ads. We'll do that. We'll get our total of 91. And then now sum of squares. All right, so in this case, we need to square each of the individual observations and then sum those in each column. And then we'll take the total of those. And there we have that, sum of the squares, 451. Okay, so now we're going to do some intermediate calculations. pretty similar to last week, some differences, but the underlying, I guess, premise is the same in terms of the basic flow of what we're doing. So first, compute a correction factor by squaring the grand total and dividing by the total number of observations, right? And so again, the key thing here is to pay attention to this notation. We are referring to the square of the grand total, not the sum of squares, right? A very minor difference that will have profound impacts on the results that you calculate. I've seen it happen several times, so I want to be clear. Just pay attention to that notation on the first step of stage 2. And then we will start adding or dividing things here. And you know, and I'm not going to spend too much time explaining all this. As per last week, pay close attention to values that are listed on the slide here in the notation to make sure that you get things right. And so divide the sum of squared person scores by the number of groups. Yeah, and so the key thing here is that the sum of P here is referring to the sum total for each person, right? So in this case, this first value, 12, we acquire that by adding 2, 5, and 5, and we find a value of 12. So we take 12 squared divided by 3, because 3 is the number of groups, right? So P squared over K. Here, P just refers to each person score, right? So that's where that's coming from. Compute the sum of squares. Again, these are referring to the values obtained at step 2 and step 1 in stage 2, so on the previous slide. So if I go back to stage 2, step 2, I should see a value of 427. Let's go back. Yep, there you go, 427. Right, so that's where those are coming from. And so you can go and follow the directions on the slide to get there. And then at that point, we've calculated most of our table, right? We've calculated all of this, and then we just need to do some basic division to get our mean squares and our F obtained. And when we do that, we will find an F obtained of 17.38, and that is very significant, right? So we're going to decide to reject the null hypothesis, simply because we compare our obtained to the critical, and here you can see our rejection region. Our critical value of F was 3.89, and so our F obtained is way, way higher than that, right? So this is very obviously significant. We can very obviously reject the null hypothesis. Yeah, and so we can say that there are some significant differences between these groups, right? And so now we need to conduct a post hoc test to understand that further, right? Because you'll recall our flowchart. If we have a non-significant result, we retain the null, we're just going to stop because it doesn't matter. We don't need to look any further. But if we find a significant result and reject the null, we need to do post hoc tests. And so here we're going to do the Bonferroni procedure. I say that weird, Bonferroni. Yeah, and this is helpful because it adjusts the alpha level or the probability of committing a type 1 error for each test, simply because we're doing multiple comparisons across these groups. And so this procedure accounts for that when we are thinking about significance in our alpha. Yeah, that way we don't overinflate our, what's the right way to say this? Basically, that way we don't make a mistake unintentionally. That's the easiest way to say it. Since we're looking at this multiple different times, there are multiple different ways we can screw up, and so this accounts for that. There you go. Nice job, Kevin. Thanks. Yeah, and so test-wise alpha level for each test. Yeah, you can look at this further if you want. But simply in Bonferroni, we'll calculate that by doing experiment-wise alpha divided by the total number of pairwise comparisons. So in other words, if our overall alpha is 0.05, we're going to divide that by the individual number of comparisons we're making, and then that will be our test-wise alpha, or the alpha for each specific comparison. And so let's follow these steps here. First, calculating that test-wise alpha. So first, we're going to calculate our means for each of the groups of conditions. And so we get that here, and then now we need to do comparisons, right? So first comparison is generic Q and no Q. And I should say it's kind of arbitrary in what order you do this. This is the general flow that I follow here. The key thing is to be consistent with what you're doing. That way you don't get lost in your interpretations. Yeah. So doing these comparisons, we see our mean differences of 1, 2, and 3. That's pretty convenient. And calculating testwise alpha, so we have 3 comparisons, so we'll take 0.05, the overall alpha, divided by 3, and we'll get a value of 0.02 if we round, because that's like what, 0.01667 or something like that. And then we'll look at our t table to find our critical value based on our degrees of freedom. We had 7 participants, minus 1 is 6. We use that to find our critical value of t of 3.143. Okay, and so now we're just doing basic t-tests, looking at our critical value of t and our t obtained. And to calculate t obtained, we will use this formula here, where we are assuming that the population mean is 0, right? Assuming the value in the null hypothesis, or assuming the value stated in the null hypothesis, right? So basically then it's going to be the mean difference score divided by the standard error, right? And so we do that, and then we'll find these 3 t-values, and we will retain the null for the first one based on our critical value, but the final 2 comparisons are greater than that t-value, right? Minus 3.378 is outside of the rejection region. In other words, it's further to the left in this case than minus 3.143, so we'll reject the null. Same thing for this one. And then we can also look at effect size to interpret this a little bit further. At this point, you know what effect size is. The statistics we're calculating are slightly different. So here, partial eta squared and partial omega squared. We don't need to get into the technicalities there. Just note that the formulas are a little bit different, but we'll interpret this the exact same way. So whatever percent of the variability in the dV can be accounted for by the factor, right? And so if we calculate partial eta squared, we'll get a value of 0.7425 following this formula. So in other words, 74% of the variability in advertising effectiveness can be accounted for by the Qs in the ad, right? And so yeah, a couple different ways to calculate partial omega squared. I'm not going to focus on it because in your exercises you'll use partial eta squared. But wanted to mention that these are here for you if you do need them, such as for the quizzes or anything like that, or just for your own curiosity. And so to kind of wrap this up here, to interpret this, this is one example of how we could write this out. So we could say the one-way analysis of variance for each significance, F to 12, again, pay attention to which degrees of freedom we're reporting here, equals 17.38, P less than 0.05, partial eta squared equals 0.74. And then using the Bonferroni procedure, related samples t-test showed that ratings of effectiveness were significantly greater for the ad with smoking-related cues compared to the ad with generic cues and the ad with no cues, right? And so pay close attention as you're interpreting those t-tests and the hypotheses to make sure that you're understanding these comparisons correctly, right? And so for each significant one, look at the specific comparison and identify, okay, which mean score is higher than the other, therefore which one is significantly greater than the other, right? Or maybe significantly less than the other, however you're framing it in the context of the question. And there you have it. We'll go ahead and stop there, hopefully a little bit shorter and sweeter. We'll see you next time.